Hello, this is the section 6.5 lesson. For this section you're going to need table A2, which we printed in the previous section. In this section we're going to introduce a very important theoretical concept called the central limit theorem. It also has its practical applications as well. To illustrate one of these practical applications, let's look at this example. A water taxi has a safe passenger load of 3,500 pounds. That means it can hold 3,500 pounds of people. If the people weigh more than 3,500 pounds, then the boat will be unsafe and possibly sink. One question we might ask is just how many people can the boat hold? If I have a group of people, it's difficult to weigh all of them and determine if they weigh more than 3,500 pounds. But if I have a maximum number of people, it's very easy to determine if this group of people can fit on the boat or not. So to do our calculations, we're going to assume that people weigh an average of 174 pounds. So if we take 3,500 pounds divided by 174 pounds per person, we come up with 20.11 people. So we'll round that off to a limit of 20 people. So on our boat we might put a sign that says maximum of 20 people. Well, let's make a quick observation here. If the mean weight of 20 people that I put on the boat is 175 pounds or greater, then the boat will be overloaded. That's true because our maximum number of 20 people was calculated based off a mean weight of 174. If they weigh on average more than 174 pounds, then the boat's going to be overloaded and there's going to be problems. So here's a question we need to answer. What's the probability that the mean weight of 20 people is 175 pounds or greater? If this probability is very small, like 0.0001, then we'll say, well, that's probably an acceptable risk. That's a very small probability that 20 people are going to weigh more than 175 pounds on average. That's an acceptable risk. However, if that probability is high, like 0.2 or 0.3 or higher than that, then we'll say, well, there's a good chance that the boat's going to be overloaded with 20 people, and so maybe I need to decrease that limit of 20 people. So let's make a couple of other quick observations here. We have a procedure. When we load the boat, we have a procedure. That procedure is that we're randomly selecting 20 people to put on the boat. An outcome of that procedure would be a sample of 20 people. Each one of those samples that I put on the boat will have a mean x bar, a sample mean x bar. So with each one of these outcomes, I have associated a real number called the sample mean. So therefore x bar is a random variable for this procedure of loading the boat with 20 randomly selected people. What we're asking in our question is a probability of this random variable. We want to know what's the probability that this random variable is going to be greater than 175. So to answer our question and do our calculations, we're going to use this central limit theorem. It says, suppose we take random samples of size n from a population with mean mu and standard deviation sigma. So n is our sample size, our population mean is mu, and population standard deviation is sigma. Central limit theorem tells me three things about x bar, our sample mean. First, x bar has an approximately normal distribution. That means I can use a bell curve to calculate probabilities of x bar. Second, the mean of x bar, which is denoted by mu sub x bar, is equal to mu, the population mean. Third, the standard deviation of x bar, which is denoted by sigma sub x bar, is equal to sigma, the population standard deviation, divided by square root of n. So central limit theorem tells me my distribution of x, its mean, and its standard deviation. Using that information I can calculate means, probabilities of x bar. Okay. So to calculate our probability here, we're going to use some real data. Assume the weights of people are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. So this is our population that I'm interested in. It's all people. Our population mean mu is 172 and the standard deviation is 29. Okay. So let's define our variable here, x bar. is the mean weight of 20 people. It's a good idea to define your random variables before you start calculating so that you have a good idea of what you're working with. Our central limit theorem tells me three things about this random variable. First, x bar is normally distributed. The second is that the mean of x bar equals our population mean, which is 172. Third, the standard deviation of x bar is sigma divided by square root of n, which is 29 divided by the square root of 20. If I do that arithmetic on my calculator, it comes out to be 6.94. So x bar is a normally distributed random variable, has a mean of 172, and a standard deviation of 6.49. So the question I want to know in mathematical terms is the probability that x bar is greater than 175. Again, that random variable is normally distributed, has a mean of 172 and a standard deviation of 6.49. So I'm working with a non-standard normal distribution problem. The first step in a non-standard normal distribution problem is to convert everything over to z-scores. So I need to convert that number inside the parentheses over to a z-score. So I take the number 175 minus the mean of 172 and divide by the standard deviation of 6.49. I do that arithmetic on my calculator, it comes out to be 0.46. So now, the probability that I want, that x bar is greater than 175, equals the probability that z is greater than 0.46. Again, just like in last section, we went from a non-standard normal distribution problem over to a standard normal distribution problem. So on my bell curve, my standard normal bell curve, I draw 0.46, a vertical line I shade to the right because I'm interested in z greater than 0.46. I go to my z-score table, the area to the left is 0.6772, subtract that number from 1, and I get my probability there, 0.3228. So there's my answer. The probability that the mean weight of 20 randomly selected people is greater than 175 is 0.3228. So let's state a conclusion here. There's a good chance with probability of 0.3228 that the boat will be overloaded with 20 randomly selected passengers. That's a very high probability. That's much greater chance than we probably want to take. So therefore the limit of 20 passengers should be decreased. Now just how much should it be decreased is a bit subjective. Should it be decreased down to 19, or do we need to go down to 18 or 15, or what's a low enough limit? Doesn't matter how low we set the limit, there's always going to be some probability that their mean weight is greater than 175. So there's always going to be some chance that the boat is overloaded. Determining just how low that chance should be is a whole other topic. Now, with this formula, the central limit theorem, as with every other formula that we're going to get for the rest of the semester, there are some requirements that have to be met. I can't simply plug any numbers into any formula and expect to get a valid result. There have to be some requirements met. So to use the central limit theorem, first we must have a random sample. What that means in terms of this example is that I can't pick my 20 people from a football team, nor could I pick just a bunch of supermodels. The people I pick need to be a random sample of the entire population. As we mentioned back in chapter 1, if I don't have a random sample, there isn't a whole lot that I can do with the data that I collect. The second requirement is that the population needs to be normally distributed or n is greater than 30. Now in this case my population was normally distributed, so it doesn't matter how big n is. But if my population is not normally distributed, then I need a sample of bigger than 30 in order to apply the central limit theorem. In our next example, we're going to illustrate the difference between a regular non-standard normal distribution problem and a central limit theorem problem. So the heights of women, the heights of the population of women are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Okay, so they're dealing with a non-standard normal distribution. We're going to calculate two different probabilities using this information. First, the probability of selecting a single woman whose height is greater than 72 inches. And then part B, the probability of selecting a sample of 20 women whose mean height is greater than 72 inches. 72 inches is of course 6 feet. So the first one, we know the probability of selecting a single woman greater than 6 feet. Part B, the probability of a sample of 20 women whose mean height is greater than 6 feet. Okay. So in part A, if we let x equal the height of a single woman, I want to know the probability that x is greater than 72. Now notice here our variable is not x bar because we're not dealing with the mean of a sample. This is just the height of a single woman. So I want to know the probability that x is greater than 72 inches. I'm told it's normally distributed with mean 63.6 and sigma 2.5. So this is a regular, non-standard, normal distribution problem. So I first need to convert my x value over to a z-score. So take 72 minus the mean divided by the standard deviation. Comes out to be 3.36. So then the probability that x is greater than 72 equals the probability that z is greater than 3.36. On my bell curve, I shade to the right of 3.36. From my table, the area to the left of 3.36 is 0.9996. Subtract that from 1, and I get my probability. So there we see that probability is about 0.04%. That's the probability of selecting a single woman that is greater than 6 feet tall. In part B, we want to know the probability of selecting a sample of 20 women whose mean height is greater than 72 inches. Now notice the difference between this problem and part A. Here we're asking for the probability of the mean of a sample. We're not dealing with just a single woman. So whenever we're asking about the probability of the mean of a sample, we're going to use the central limit theorem. So my variable here is x bar. It's the mean height of 20 women. By the central limit theorem, first of all, x bar is normally distributed. Second, the mean of x bar equals my population mean of 63.6. And then third, the standard deviation of x bar is sigma divided by square root of n. N is 20 in this case, and so the standard deviation is 0.559. Okay. Now the probability that x bar is greater than 72, again that's a normally distributed random variable with mean 63.6 and standard deviation of 0.559. I need to convert that number 72 over to a z-score, so take 72 minus the mean divided by the standard deviation, and I get 15.03, which is a huge z-score. Okay. So the probability that x bar is greater than 72 is the probability that z is greater than 15.03. So I want the area to the right of 15.03. Now if I look at my table, it says that the area to the left of 15.03 would be 0.9999. Actually, it's greater than that. And so the area to the right is 1 minus that number, which would be 0.0001. Actually, it's much smaller than that. So there we go. There's a probability that the mean of a sample of 20 women is greater than 72. That probability is 0.0001, or actually less than that number. So again, this example illustrates a difference between a regular non-standard normal distribution problem and a central limit theorem problem. In a regular problem, we're dealing with the mean of a single person or a single member of the population. In a central limit theorem problem, we're dealing with the mean of a sample. Okay. So what we can conclude by comparing these two results is that the probability of selecting a sample of 20 women whose mean height is greater than 72 inches is less than the probability of selecting a single woman whose height is greater than 72 inches. That's it for this lesson. The Course Compass homework is titled Section 6.5.